Welcome to Rigorous Motion. In this episode, a tour of the sequences every analyst knows by heart. Powers and roots tamed by limits, the number E, the golden ratio, Euler's constant, and the runaway growth of the factorial. Throughout this tour, the word converge will mean one simple thing. A sequence converges to a value L when its terms eventually gather near L and stay. Choose any tolerance, a small interval around L. Past some point, every single term lands inside it. Tighten the interval as far as you wish. The terms always catch up and crowd in, never to leave again. Keep this band in mind. Every story that follows is a race to get inside it. We begin with the simplest family, 1 over n, raised to a positive power, p. Start with p equal to 2. With the square in the denominator, the terms collapse towards 0 almost at once, dropping like a stone. Now a gentler power, 1/2. The root in the denominator fades far more slowly, yet, given enough terms, it too sinks towards 0. Whichever positive power you pick, fast or slow, the terms are eventually trapped inside any band hugging 0. The exponent only sets the pace. Now let us prove it precisely, using only the definition of a limit. Fix a tolerance, call it epsilon, above 0, and ask when the term falls below it. The term lies below epsilon exactly when n to the power p climbs above 1 over epsilon. And taking pth roots, the requirement becomes simply that n exceed one fixed threshold. The Archimedean property guarantees an integer past that threshold, and every later term then lands to the left of epsilon. By the definition of a limit, the sequence converges to 0. A positive power in the denominator always wins. Smaller powers merely take their time about it. Next, fix a positive number and take its higher and higher roots. Take the number 4. Its square root is 2, its cube root is smaller still, and each further root sits closer to 1. The values descend steadily toward 1. Start instead below 1, with 1/4. Now the roots rise, approaching 1 from underneath. Either way, 1 is the destination. Now to prove it, take p above 1 and name the gap above 1. D sub n, so the root is 1 plus that gap. Bernoulli's inequality says 1 plus d raised to the n is at least 1 plus n times d, but the left side equals p itself. Rearranged, the gap is caught between 0 and p minus 1 over n, which marches to 0. The squeeze theorem from before forces the gap to vanish, so the root is driven down to 1. For a number below 1, write its root as 1 over the root of its reciprocal. That reciprocal exceeds 1, so its root tends to 1, and the algebra of limits returns 1 once more. The higher root is a great equalizer. Hand it any positive number at all, and it returns 1. Here is a small marvel. Take n itself and extract its nth root. The first values actually rise, the square root of 2, then the cube root of 3, which turns out to be the highest point of all. After that peak, the values turn and descend, pressing ever closer to 1, even as n races to infinity. Now, rigorously. Since n is at least 1, its root is at least 1, so write the root as 1 plus a non-negative piece, which we name delta. Raise 1 plus delta to the n with the binomial theorem. Every term in the sum is non-negative, so we may keep only the third term and discard all the others. That term alone is n times n minus 1 over 2 times delta squared, while the left side is exactly n itself. Solving, delta is caught between 0 and the square root of 2 over n minus 1. That bound collapses to 0, so by the squeeze theorem, delta vanishes, and the root settles on 1. However fast n grows, its own nth root settles on 1, with a single high point at n equal to 3. A contest now, a power of n pitted against a growing exponential. Let the polynomial be n squared, and the exponential have base 1.5. At first the polynomial leads in comfort. Squaring easily outpaces a modest base. But the exponential compounds upon itself. Slowly it gathers speed, and around the 13th term it draws level with the polynomial. Past the crossing, it erupts upward and never looks back, leaving the polynomial infinitely far below. So the ratio of polynomial to exponential collapses to 0, and the same holds for any power at all, and any base above 1. Now the rigorous version, for any power alpha and any base above 1. Choose a whole number k larger than alpha. A single term of the binomial expansion already bounds the exponential from below. 1 plus p to the n is at least n choose k times p raised to the kth power. Once n passes twice k, each of the k factors in that coefficient exceeds n over 2, so the coefficient outgrows n to the k over 2 to the k times k factorial. Substituting, the ratio drops below a fixed constant times a power of n with a negative exponent. And we proved at the very start that a positive power of n in the denominator tends to 0. The squeeze then finishes the argument. No fixed power can keep up with steady exponential growth. In the long run, the exponential wins by an unbounded margin. Multiply a number by itself again and again. If its size is below 1, the powers shrink geometrically. Take 7/10. Each step keeps 7/10 of whatever remained, so the terms melt towards 0. Make it negative, and the terms alternate sides while still contracting, spiraling into 0 from both directions. Everything hinges on the size staying below 1. At exactly 1, the terms never move, and beyond 1 they escape upward without bound. And the proof needs no fresh work at all. Since the size of x is below 1, its reciprocal exceeds 1. Set p equal to that reciprocal minus 1, a positive number. Then the size of x to the n is exactly 1 over 1 plus p to the n. That is the previous limit, with the power alpha set to 0. By the result we just finished proving, it tends to 0, and so x to the n tends to 0 as well. Inside the unit boundary, the powers vanish. On it they are stuck, and outside it they explode. Now a number that runs through the whole of analysis. Invest $1 at 100% interest, but compound it n times across the year. Compounded once, you simply double your money. Twice, you do a little better. More often, better still. The gains climbing steadily as n grows. Yet the growth never runs away. An upper companion sequence presses down from above, and the two together trap a single value between them. That trapped value is e, 2.718, and onward forever. The limit you would reach by compounding continuously, every instant. Now to prove the limit exists, and bound it on the way. The binomial theorem rewrites the nth term as a sum, 1 over k factorial, times a product of factors each below 1. Every factor is at most 1. So the sum is at most the reciprocal factorials, which a geometric series of halves keeps strictly below 3. The sequence is bounded above. Going from n to n plus 1, every factor grows, and a fresh positive term joins, so the sequence strictly increases. Increasing and bounded, the monotone convergence theorem, from an earlier chapter, secures the limit. We call it Euler's number. This one constant anchors continuous growth, the natural logarithm, and a vast amount of mathematics besides. From an old rabbit puzzle comes a sequence everyone has met, 1, 1, 2, 3, 5, 8, with each term the sum of the two before it. Lay down squares with these side lengths, and they whirl outward into a golden rectangle, each larger than the last by one fixed proportion. That proportion reveals itself in the ratios of neighboring terms. Watch them land, above, then below, then above, closing in on a single number. The number is the golden ratio, 1.618, exactly 1 plus the square root of 5, the whole divided by 2. It obeys a striking rule. It equals 1 plus its own reciprocal. So its continued fraction is nothing but ones, which makes it the hardest of all numbers to approximate by simple fractions. Now to prove the ratios converge and to pin down their limit. Each ratio is 1 plus the reciprocal of the one before it, straight from the Fibonacci rule. If they approach a value L, that value must equal 1 plus its own reciprocal, whose positive solution is the golden ratio. To show they truly approach it, subtract the golden ratio. The error flips its sign and is divided by the golden ratio times the previous ratio. Since every ratio is at least 1, that divisor exceeds the golden ratio, so the error shrinks by a factor below 1 at each step. The error is geometric, and a geometric sequence with ratio below 1 tends to 0, exactly the limit we proved earlier. So the error vanishes, and the ratios lock onto the golden ratio, alternating above and below. Successive Fibonacci ratios swing above and below the golden ratio, drawing tighter around it with every step. 4,000 years ago, scribes computed square roots with a trick we still use. To find the square root of 2, guess a value, then average your guess with 2 divided by it. If the guess is too large, 2 over it is too small, and their average lands between, nearer the truth. Then repeat the step. Begin at 2. One step gives 3 halves. The next, a value correct to 2 decimals. The next, correct to 5. The staircase spirals straight into the corner. Now to prove it really reaches the square root of 2. First, by the inequality of arithmetic and geometric means. Every term from the first is at least the square root of 2. Second, the difference of consecutive terms is 2 minus a squared over twice a, which is never positive. The sequence decreases, decreasing, yet held above by the square root of 2. The monotone convergence theorem guarantees that the sequence converges. Letting n grow inside the recursion, the limit equals 1/2 of itself plus 2 over itself. That forces its square to be 2, so the limit is the square root of 2. And the speed has a clean explanation. The error at each step is the previous error, squared, divided by twice the term. So the count of correct digits roughly doubles at every single step, a blistering rate known as quadratic convergence. And this is no accident. Averaging in just this way is precisely Newton's method, applied to x squared minus 2. An algorithm older than the alphabet converges so fast that a handful of steps already pins the root to many decimals. Add the reciprocals of the whole numbers, 1 plus a half plus a third, onward. These running totals are the harmonic numbers, growing without bound, but agonizingly slowly. Picture each reciprocal as a bar of width 1. Stacked together, the bars overshoot the smooth area beneath the curve 1 over x, an area equal to the natural logarithm. The slivers of overshoot, summed across every bar, do not pile up forever. They converge onto one mysterious number. That number is Euler's constant, written gamma, roughly 0.5772. And here is the astonishing part. Gamma threads through analysis and number theory. Yet to this day, nobody knows whether it is even rational or irrational. Let us prove the gap truly settles. Call the gap C sub n, the harmonic number minus the logarithm. From one step to the next, the gap drops by the area between the curve and a horizontal level, which is strictly positive, so the gap decreases. It also stays above 0 because the bars together overshoot the area, making the harmonic number exceed the logarithm. The gap is positive. Decreasing and bounded below, the monotone convergence theorem, yet again, secures the limit. We call it Euler's constant, gamma. A constant as fundamental as pi or e, still guarding the simplest secret of all, whether it is a ratio of whole numbers. Take two positive numbers, 3 and 2. Raise each to the n, add them, and take the nth root. Where does the result settle? The first value is 5, yet it falls fast, heading toward 3, the larger of the two bases. Now, rigorously, take it to be the larger base. The sum lies between a to the n and twice a to the n, and taking nth roots preserves that order. The lower end is itself, here exactly 3. The upper end is a times the nth root of 2, and the nth root of 2 tends to 1, a special case of the root limit we already proved. Both ends approach a, so by the squeeze theorem, the sequence is pinned to a, the largest base. The others leave no trace. Under the nth root, only the biggest base survives. With more numbers, the same holds, the maximum always winning out. We end with a theorem that ties the whole tour together, due to Cauchy. Take any sequence that converges to some limit. Picture its terms wobbling as they home in on the limit. Now replace each term by the average of every term so far. The averages run calmer, the wobble smoothed away, and they settle on the very same limit. Here is why the averages must converge, made precise. Fix epsilon. Pass some index n, every term sits within epsilon, over 2 of the limit. Split the deviation of the average into the early terms, up to n, and all the later terms. The early terms form a fixed total divided by n, which melts to 0, while the later terms already lie below epsilon over 2. For large n, the average is within epsilon of the limit, so the arithmetic means converge. Taking logarithms turns products into sums, so the identical argument settles the geometric means as well. From the geometric mean version flows a powerful corollary. If the ratio of consecutive terms tends to a value, then so does the nth root of the term, since that root is the geometric mean of the ratios. Aim this corollary at a clever target, n factorial over n to the n. Its consecutive ratio simplifies to 1 over the compounding sequence we met earlier, whose limit is the reciprocal of Euler's number. It follows at once that the nth root of n factorial, divided by n, tends to 1 over e. Said plainly, the factorial grows essentially like n over e, raised to the nth power. One theorem, and the growth of the factorial drops out, beside the nth root of n from before, a fitting place to close the tour. 11 sequences, gathered in one view, powers and roots tamed to 0 or 1, the constants e, the golden ratio, and gamma, an ancient square root, the dominant base, and the soaring factorial. If following these stories made the limits come alive, a like and a subscribe truly help, and carry the next chapter to more curious minds. Thank you for exploring them with us.